So I'm going to be talking about large captured satellites and natural satellites, exomoons. And just briefly, we've talked a lot about Kepler in this session. And these are all the results as of the last AAS so far. And you can see there are tons of planets they're getting, but they can all, when we get out here in the habitable zone, they start to get fewer and fewer because you get fewer and fewer transits. It's harder to detect. So most of the planets we actually know about that are out in this region, with similar temperatures to Earth, are much larger than Earth. They're giant planets. And really didn't expect this before. 10 years ago, people said you're crazy if you thought there were so many giant planets out here, but there are tons of them. There aren't the majority of planets in there, but there are lots of them there. And we know that they're there. So, potentially, if we want to try and find habitable places, this sounds like a good place to start. Especially if they're big enough, they might have satellites that are large enough to be habitable. In order to be habitable on the surface, you need to be at least somewhat as large as Earth. Mars, astronomers somewhat as large, so within order of magnitude of the size of Earth is what we're talking about here. But that's still pretty hard for the satellites in our solar system. So you need something quite large to do that. But if you look at the natural satellites in our solar system, the largest one is Ganymede. It's just a little bit larger than Mercury, which means it's quite smaller than Earth. The only one of them that actually even has an atmosphere is Titan, and that's because it's so cold. Titan wouldn't keep its atmosphere if it were as close to the sun as Earth is, simply because it just get too hot and it would escape away pretty fast. So it's really hard to have a large satellite close into a star. It gets the dynamics of how it accretes around the planet just make it so that you're not going to get naturally forming satellites around the planet that are much larger than Ganymede, even if you have a much larger giant planet to start out with. So it's sort of tricky to get much better than this unless you start to look at other means of having satellites. And when we say regular satellites, these are satellites that formed from a circumplanetary disk, like the disk around the star to begin with, but it's around the planet, and they form a little miniature solar system. Irregular satellites are objects that formed somewhere else. Somewhere else is usually, for the giant planets, meaning on the Kuiper Belt region, but it can also mean asteroids as well, which come in and then afterwards get captured. And afterwards is still a long time ago, solar system-wise, but it was still after all the planets and everything had formed, and then as things were sort of dynamically evening out, these captures happen. We've only been to one of these irregular satellites, and that's Phoebe, because they tend to be in very wide orbits, very, sort of eccentric at the edges sort of thing. And that's how we can tell that they've obviously been captured, because you have to have been captured to be there. They're probably much closer in satellites, but they were also captured. We just can't tell that they're captured because they've sort of evened it out. And one of the ones that's evened out quite a bit, but is still obviously a capture, is Triton. Now, most capture satellites are very small. This is the largest of the Saturnian capture satellites, and this is only a couple hundred kilometers across. Whereas this guy here is about the size of our moon, so it's about 3,000 kilometers across. And it's the only large satellite of Neptune. All the other giant planets have sort of nice little systems of, Jupiter, Saturn, Uranus, all of these nice systems of regular satellites. Don't have that on Neptune. Neptune, you just have Triton and a few very, very small guys. So, and Triton is in this retrograde backwards orbit.
So the only story that makes sense here is that you used to have a regular satellite system.
And then something happened such that Triton came through, bulldozered through away all of those regular satellites that were much smaller than it, and just left itself. And in that way, you end up sort of trading up, because you start out with a much smaller satellites and end up with something that's quite a bit larger. Thankfully, we have actually been to Triton. This is a bit of a synthetic image, but you can actually see these little streaks on there. Those are actually little plumes of nitrogen that are trailing up dust onto the surface. So this is an active dynamic surface out at the edge of the solar system.
Simon, your mic slowed down here.
Oh.
We have on your shirt, not the string.
All right. Can you hear me? Okay. So what we think probably happened to cause this capture event was that giant planets migrate. And if you've not been following planetary science, this is the most revolutionary thing that has happened in solar system science in the past 10 years, is this realization that the giant planets are, in many cases, nowhere near where they were when they actually originally formed. And when we used to map out what the protoplanetary disk looked like, we just kind of assumed all the planets were where they were, and then we just sort of spread out that material and said, okay, it's a disk. In reality, they're much more compact. We had a much more massive disk. So they're all very close in, and Neptune actually probably was inside of Uranus. And then Jupiter and Saturn got into mean motion resonance with each other. They kind of moved it around a little bit, you can see there, but they really moved around the smaller of the two giants. And so Neptune swapped places with Uranus and went out into this big disk of material, which is the proto-Kuiper belt, and dissipated most of it. And in the process of dissipating it, it encountered a lot of things. And one of those that it encountered was Triton. It's probably the largest thing it actually had a close encounter with. And Triton got captured and bulldozered away all of the original satellites of Uranus and just left itself. So, oh, there's supposed to be a picture there, but it's gone. Oh, never mind. So, planets migrate, and this migration happens both ways. In our solar system, it happened in outward motion. With missions like Kepler, we're starting to get all the migrations that happen inward. So this can go in both directions. And the giant planets come in, they can go out. And when they're migrating, they're encountering lots of objects that were there previously, and you can have these captures occur. But to have a capture, you need to, it's an angular momentum switch, right? Because if you're coming in at a hyperbolic orbit, when you're approaching a planet, you're going at least parabolic, if not hyperbolic. You have as much energy going out as you came in with, if nothing happens. So what you need is some sort of an event when you're close to the planet, which causes you to lose a little bit of energy and trade angular momentum with the system. And the two ways you can do this. One is that you already have a satellite and you get rid of it along the way. So this is what the method that is most commonly given for the capture of Triton, is that you have Triton and then you have maybe a satellite, and it comes in close, and the motion of the two objects themselves together is hyperbolic. But then when they get close here, one's going a little bit faster than hyperbolic, and one's going a little bit slower. So then right at closest approach, you kick off one of them, and it goes off really fast, and the other guy is going much slower, and it gets captured into elliptical orbit around here. So that's a really clean, it's a very neat way of doing it. Unfortunately, you have to presuppose that you have a satellite on there, which makes it a lot more complicated then, because it's a two-stage process. The other way to do that is to say that you already have a satellite around the giant planet, which makes sense because all the giant planets have many satellites. And you actually swap places with that. Now, it's a much smaller cross-section to do this. You need to be just just right to get in there. But you know, you have much more satellites to work with. So potentially this is a much more effective method. So, so this is a case here where you're coming in, and so the squigglies there are the small satellite around one of the large objects, the red object, and then you got the blue here, which is the other large object, and they get close here, and then this small guy absorbs most of the momentum of the system and just gets tossed out of there at like 10 kilometers a second. It's just zooming out. And so it's taking away all this momentum, and they get trapped into a nice elliptical orbit around each other. And you let that go long enough, and they'll actually circularize to something that's nice and stable. So I meant to do a bunch of simulations that, for various reasons, didn't happen. But the simulations that I've done so far, mainly with this first method, and those with the REU student the summer before last, where we were just sort of making synthetic systems where you had an Earth and a moon, or Earth with a moon that's the size of Mars, or Mars with a moon that's the size of our moon, and just kind of toss that at a giant planet and see if it captures or not. And, you know, in general, we were getting sort of captures maybe sort of 5% of the time, and some, you know, depending on the circumstances, up to 20% of the time. So, you know, it's not that it happens every time there's a close encounter, but it's not incredibly rare either. Now, of course, you can see here the most common outcome for most of these was that there was an impact. So the most common case, the large one impacts, or maybe the smaller one impacts. But the red line there is the actual capture event, and it does happen. It's more likely in these cases that the larger of the two captures, which is good. And then we've all, you know, when they capture, they always capture into very eccentric orbits, but they don't stay that way because eccentric orbits are not stable when you're near something. So their body tides circularize them pretty fast, and they circularize, and they're tidally locked. You know, we've been talking about tidally locked a lot today, but they're tidally locked to the planet. And they tend to be in orbits that are a couple days. So, you know, as far as illumination is concerned, you know, they're seeing the sun just as often as they would if they were, you know, in a 24-day rotation period at 1 AU. And in fact, if you were on the far side of one of these exomoons, you'd never know that you were in orbit around a giant planet because you'd never see it. So they get, you know, about 50% of them that end up captured are sort of, you know, circular as well. And the circularization happens fast. This happens in about 1 million years. So they get a lot of heat. They're like Io very briefly. They get a lot of heat, you know, in this pulse. But they're also bulldozing away all the other moons. Io has heating there because it's interacting with the other satellites in the solar system, in the Jupiter system. If Triton doesn't have that, and we're looking at cases more like Triton, where it's bulldozing away everything else, and you're just left with that one. So you're not going to have long-term tidal heating in these. Any heating interior is going to be radiogenic, long-lived stuff. And finally, are they detectable? Probably, but you need a lot of transits to tell. With the first few transits, they're just going to be off a little bit, and it's going to look like noise in the data. You need lots and lots of transits to tell. And it's only the furthest most of the exoplanets that we can actually do this for. So 7+ transits for something as a 1 AU around a solar-type star, that takes 7 years. It's going to take a little while before we start to get these exomoons because we just need lots and lots of transits. And so just wrapping it up, exomoons are potentially large enough to be habitable. The ones that are potentially habitable are the easiest to detect. So if we hear about any exomoons within the next 10 years, they're going to be ones we want to look at for habitability. You know, to capture these, there are a couple of different ways to do it. So training up satellites is potentially the most effective way to do it. And then once you're captured, you have about a 50% chance that the tides will stabilize everything out. Thank you.
So what does that sudden peak in tidal heating mean for habitability? So if there was life before, would it be completely sterilized from that capturing process?
Probably, but it's also, I mean, we're talking about like a couple of million years after the disk dissipation, so that would be before life, the earliest evidence we have for life on Earth. This is sort of the same time scale as the moon forming impact on Earth, which was a sterilization event. So yeah, you can think about it the same sort of, it's actually less dramatic than the moon forming, because the moon forming impact stripped the entire surface. This would just heat up the surface, but only for about 1 million years.
Did you mention that you had any candidates?
So they've been looking. So this is Kepler data for one that they thought was, and it turns out this was actually an unseen, non-transiting planet that was causing these timing variations. But this search Nisvorny and Kipping were doing was looking for them, and it's eventually going to look like that, but we're going to need a lot more. And this one, you can tell this is days on the bottom there, so this is a very large variation. The variations we're going to probably looking for the habitable exomoons are sort of 5 to 1 minute type variations. So you need really good data and you need lots of it to be very confident that you're going to see it. But potentially, it could be there in the Kepler data if we mine it enough. It's really computationally intensive to do, though.
So is there some sort of minimum ratio for satellite exchange? Like, do you have to have a Mars-sized satellite initially for an Earth-sized satellite to take its place?
There's not a minimum ratio, but the closer the ratio, the higher the cross section for it. But yeah, for that case, the small guy there is 100th of the mass of the other two guys. So he's zooming off there at about 50 times their approach speed from beforehand.
We'll go ahead and call it there. Thanks very much.